It's just wonderful to be here amongst you all. Such a diverse, interesting group of people. But it's also, for me, really special to be back here in Nottingham, where not only does everyone talk like me, but also this is where I did my PhD. So I've been in this field for quite some time now, because I finished my PhD in 1981. This is what I said I was going to talk to you about the revolution in plant breeding that's being driven by genome science and about our knowledge of plant and crop genomes. Obviously, I can't talk about all the crops, and I will be focusing on one in particular, on wheat. But obviously, this is happening throughout the plant breeding industry. But the science is only one part of it. And I know one of the things that we're going to be discussing throughout this session is, okay, so we do the science, but will these opportunities that the science brings actually ever reach the market so that you'll be growing them on your farm and you'll be eating them on your plates? So it's election day. So I thought talking about the revolution probably wasn't a bad idea. And when I was here in 1979, which will be an auspicious date for the British people amongst you in the population, I campaigned my heart out for the Labour Party. And we know where that took us. But so I'm going to talk today about plant breeding. Plant breeding is really all about maths. And the breeder's equation is the equation by which the plant breeder lives. In order to realise these increases in yield and in other characteristics in quality which plant breeders have been delivering to us over the past decades, and also to overcome some of the new challenges we have with plant breeding, we need to look at that equation and say, what can we improve in order to increase that genetic gain over time? Can we improve the intensity of selection, the quality of selection, how accurate we are in choosing the right material? Can we improve the diversity available to the breeder in terms of what they then will be able to choose and what they will be able to select on? And importantly, can we change the generation time? Can we reduce the time it takes to bring a variety to market? So it's all about choice and time. So what has made the change? Well, it really is genome sequencing, basically at its core. But that's been supported, of course, by a revolution in IT. So we're at NIAB, we're based in Cambridge in the east of England. We're working very closely with Cambridge University Department of Plant Sciences, and we're building a new joint facility. And when the architects asked us to take a first look at what we needed, we said greenhouses, glass houses, it's our bread and butter. Absolutely, we need lots of glass houses. But the second thing was lots of computers, lots of spaces for computers. So the IT revolution has meant that plant breeders, if you like, the maths, can be done much quicker, much more efficiently, and the amounts of data that are available in terms of knowledge of the genome can be handled by the average person in the same way that we can now all handle data on our mobile phones. It's actually becoming easier to handle it in science too. We touched a bit on GM, and I like, obviously, if you look at how long I've been in this, I was there through the GM revolution, and I've always felt that one of the things that the negativity around GM has forced us to do was to look more intently at what was available in the natural variation that we have access to, and how we could access variation that we thought we could only access by GM. I never thought I'd be standing here today telling you saying this, and I think that GM is a very important tool in the arsenal, but I'm sure that the negativity has contributed to some of the more positive things that we have seen through looking at natural diversity. And of course, we have new technologies, including GM, gene editing, and related technologies, which can help us to access the gene pool more efficiently. So these are all of the tools and technologies, and I'm going to just take a look at some of them and some examples of how they've been used in breeding. So you can think about genome sequencing as being a way to look at the huge percentage of the plant genome, the information that codes for what gives you your crop. It's just a way to look at what's happening below the water, if you like. You can only really see a very small portion, the phenotype, a very, very small portion of what's going on. You change that environment, you change which genes are above and below the water, and understanding not just what's there, but how they all interact is a massive force in change. Now, those of us who work on wheat, well, it's a very complex species. It's a hexaploid. It has 21 chromosome pairs, which fall into 3 distinct sets. It has an A, a B, and a D genome, which all are originated from different grasses. The complete sequence of the wheat genome was published only this year. Although a couple of years ago, a usable sequence was published, it's only this year that we've actually had something that's comprehensive enough to be able to do some of the things which they've been able to do for years and been able to start to understand for years in rice. And so it's only now, for example, that we can start to say, you look at rice and wheat in the field, and actually, phenotypically, they don't look that different. So what is all this extra DNA in wheat doing? Is it doing anything? Can we access it? And so even though we've had knowledge of plant genomes for a while, you have to have the knowledge of the one that you're working with in order to get at the individual genes and characters that you need to in order to improve your breeding. Bred wheat shows very little genetic diversity. And so one of the things that we have focused on internationally, I would say, is to bring new sources of genetic diversity to the wheat breeder. And this has meant a massive public sector investment globally, because there is far too much risk in bringing these wild, weird and wonderful plants and technologies to plant breeding. There's far too much risk for the individual breeding company to take it themselves. They don't know which bit's going to work. And so it's been up to public funding to bring this material into the hands of the plant breeder. Although I will say at this point that there was a period in the UK when, in the 1990s, when Margaret Thatcher, who was elected in 1979, when she closed what were considered to be the near-market public institutions, the Plant Breeding Institute in Cambridge was closed. And there was a bit of a gap. It was a few years before the breeding industry realised that they had lost access to this wave of public sector material, which they were used to working with. And so they supported the NIAB Trust when they chose to sell some of their land in Cambridge for housing and to invest it in research in wheat breeding. We know that wide crossing works. Some of you will recognise some of these varieties. You may not know that they contain important characteristics, bits of DNA from wild wheat relatives, and they've been absolutely critical in delivering the varieties to them that we have today to the market. So knowing that, we at NIAB focused one of our flagship programmes on developing what we call synthetic wheat. Although I can remember the time Tom came to NIAB and said, you can't call it synthetic wheat. And he coined the term super wheat, which is not a bad choice. So wheat is the product of 2 chance hybridizations, which happened the first 100,000 years ago and the second 10,000 years ago. And it might have happened a few times, but basically not very often. So all of the wheat that we know came from Fertile Crescent, Iran and Iraq, 10,000 years ago. And so we and others, notably in Mexico, have been increasing the types of wheat that there are by resynthesizing wheat from its progenitor species. And importantly, increasing the variability in the D genome, where by looking at the genome sequence, we could see that all wheat everywhere pretty much had the same D. So we've gone back to collections from the Middle East, from Uzbekistan, and introduced new sources of D into wheat. Just a little reminder of the time it takes, and even though we are trying to speed things up, 3 to 5 years to develop pre-breeding lines, 2 to 3 years to screen them, and 7 to 10 more to put the variety on the market. We already touched on GM, so just going very quickly through GM to gene editing, which people tell us is a step change in how we will be able to use genome knowledge to manipulate the plant genome. There are some similarities between GM and gene editing, and although the end product might be different in that you can't detect anything new other than the plant's own genes when you do something by gene editing, whereas with GM you inevitably leave behind a footprint, a piece of foreign DNA. You still need similar techniques in order to get that change to happen. So to introduce the gene scissors to snip out your DNA in gene editing, you would use the similar technologies to the ones you would use for, again, one of our flagship projects at NIAB with the John Innes Centre, where GM is the only way to do this. We know that oats are resistant to take-all. We know that take-all resistance is conferred by a string of 10 genes which have to all operate together, and we've been working with the John Innes Centre for several years to introduce that string of genes into wheat and get them all to work at the same time. So there are some things that you can only do by GM at the moment, but gene editing does offer us not only a whole new suite of tools, but potentially a way to access the market, which we don't have with GM. I won't talk much about breeding methods, but this is where the maths really comes in, where the breeders use their knowledge of the genome to accelerate breeding, to look at techniques like genomic selection, which has been widely used in animal breeding, and bring it to the plant world. So again, back to election day. So do all of these changes lead us to new possibilities? And I put this in because I found it in my slide collection. I wanted to remind us that it isn't just about wheat, and it's just as important for things like kale and less popular species. So the synthetic wheat, we know we have material that's more drought tolerant, with better nitrogen use efficiency, and which has higher yields. We've had a lot of investment to generate larger populations in different ways of diverse wheat, with the objective of being able to look in that diversity for improved nutritional qualities, some of which I've listed here. It's not quite a targeted approach. This is more, let's create the variability, let's screen and see what we have there. We do have, oops, went too quickly there. I'm missing, there's a big chunk missing from my slide here. I don't know how it's happened, but we have a student who's looking at, we've heard about gluten, and we know that it's the gluten, that the celiac disease is conferred by a reaction to an epitope on a part of the gluten protein, and we have a student who's been looking at gene editing to remove that epitope, remove that moiety, but still retain the structural properties of gluten, which has always been the problem of gluten-free cereals. And I know there's other work going on globally, and I'm sure this will be one of the wins of that. I wanted to mention the market. I wanted to mention the common market because, of course, this election was supposed to be about Brexit, and now we're told it isn't, but I think it is. And I think there are some really important issues that we're going to be facing as plant breeders and as people who want to bring plant varieties to the market very, very soon. And in fact, it's already starting to happen. So when a plant breeder wants to place a variety on the market, it needs to be tested against other varieties to prove that it's distinct, uniform and stable, so that you're actually getting something new when you choose to grow it. And NIAB is the designated body which does this work on behalf of the government for the UK, and the reports that we make in a wide variety of species, including kale, are then taken over by the European Union, and you're allowed to place your variety on the common catalogue. So in cereals, etc., we do that for the UK, and then the information is passed on to the EU, which adopts it. In ornamentals, we do it directly for the Community Rights Office. And they told us 2 weeks ago that they'd been directed by the Commission to issue no more requests for work to the United Kingdom as of now, which means the ornamental work. We do all of the all-year-round chrysanthemums, half the clematis, half the roses, lots of vegetatively propagated species we test for the European Union, placing on the market, and let's let the UK leaves first, and then we negotiate what the conditions are hitting us immediately because of this issue. We've already heard a little bit about barley max, and I put it here just to say that we've been looking at this. This is something that was developed in Australia. We've been crossing it into UK barleys, and so we're saying, how can we facilitate the placing on the market of this obviously healthy and good product? I'm not going to say much about it because I know that the next speaker is going to talk about it in a bit more depth. But I put this up just to remind myself to say that it isn't just about having your IP and then placing it on the market. You've got to get the whole supply chain working in concert, from the original discovery through the breeding to the seed production and right through to the business. I love this slide because it sort of sums up my life, and it sums up a lot of the lives of people who've wanted to market GM through the years. Even when we find out that those same foreign sequences that I mentioned earlier exist naturally in many food crops, we still aren't able to place GM crops on the market in the EU, but we can take heart from some of the developments elsewhere in the world. This is a slide from Simplot, a potato breeding company in the United States, who are placing several varieties on the market now, developed with technology developed in UK universities and elsewhere. I wanted to leave you with the orange petunias. I don't know if any of you have heard about the orange petunias. Yeah? So apparently there was a Finnish scientist who was walking around his local garden centre and saw some orange petunias, and he said, hold on a minute, you don't get orange. I know a lot about the genome of petunias and how the genes all work together, and you just don't get orange, and there's only one way you could have orange petunias, and that's if they're GM. And so alerted the garden centre, and I was told this by someone in DEFRA who said, but we stopped them at the border. And I thought, oh no, because it would have been, kind of good to have harmless orange petunias there in our garden centres. But they have, as you can see from this, and if you Google it, they've gone all over the world. So I suppose one of the reasons I put that there was to say, well, obviously this is not a good thing because it's broken, it's gone against the system that we have to regulate placing on the market of these things. But maybe with Brexit, we have an opportunity to look at minor crops and to look at them in a different way in the UK to the way that the European Union has been looking at them. So I know that some of you are visiting NIAB next week. You'll be very welcome. It's a very different organisation. It too was privatised by Mrs Thatcher's government in 1996 and has no core support from government, and is actually, even though I say it myself, quite an interesting place to visit, and we look forward to welcoming you there. Thank you.